Yeah, the last thing I want to show you is feature clustering, which is also somehow in the class of randomized search. So the idea is, if I have a feature space and an unsupervised data mining task now, so this especially works for unsupervised tasks, we reduce F to a subspace K while reducing redundancy. And how do we do that? We cluster the features in the space of objects. So consider your data as a matrix. So the columns, of course, are your features and the rows are your objects, like in a relational table, for example, in a relational database system. And usually you want to cluster the objects according to the features. So if you transpose or flip your data matrix, your data table, so you have the columns, the objects as the columns and the features as the rows, you could again cluster the rows. So in that case, you cluster the features according to their object values, so to say. Yeah. So you use a clustering on the transpose data matrix, and then you get clusters of features having redundant values in all the objects, or in most of the objects actually. Problem here is very often that you have much more samples than the features, so the transpose data matrix has much more columns than rows. But okay, if you employ a very simple model or a specific distance measures, that may somehow at least ease up this problem. So here's a typical example in item-based collaborative filtering. So for example here, features 3 and 4 are similar over all persons, so they could be merged into one feature. Yeah? So if you transpose, so this is the original data matrix, if you transpose it so that you have the persons as columns and the items, in that case is the movies, as rows, and you cluster the rows, you will see that those two rows here are very similar over all columns, so over all persons, and then you can merge them to one feature, for example. So if you use, for example, k-means, and this one is one cluster, you can use the mean as a new feature. Yeah? Instead of two features you have, or instead of many features in the same cluster, you have just one feature, which is the mean of all the features in that cluster. And that's exactly how you do it. So first of all, the workaround for this many feature problem, use specialized similarity measures. For example, you can use cosine similarity, very good for high dimensional data, or Pearson correlation coefficient is very often used for that. And then you just use some partitioning algorithm, for example, k-means or k-median. K-median is maybe a little bit better because it gives you an actual, a real feature, which has been there before. The mean of several features may be hard to interpret, in the results may be hard to interpret, so k-median is maybe a good idea. So you cluster the features with k-median clustering using, for example, Pearson correlation coefficient. And then you select the medians as the new data space. So the medians of the feature clustering form your new data space, and then you can do all the other things you want to have. Yeah, and since you want to have a k-dimensional subspace, that is easy to control because k-means, k-median always gives you k clusters, so you always end up in k new features, which are the medians of the original features in the clusters. Yeah, just take care for each cluster, for each group of individual features, or of dependent features. Sorry, there's just one representative feature. Maybe a good idea or not, don't know. Depends probably on the application. And yeah, other clustering algorithms, of course, could be used. For example, approximate clustering methods for performance reasons and stuff like that. But typically you want something which has a handy easy to use cluster model like the Medoid or the mean. Yeah, so density based clustering could be employed, of course, but how do you compress the cluster? Yeah, so you are interested in compressed clusters. So compression is your somehow your meta target. So, and you probably know from KDD1 then that partitioning clustering algorithms are good for compression. So those clustering algorithms are probably a good idea to use, actually. Yeah, short discussion. Depending on the clustering algorithm, it's quite efficient. So k-means especially is very efficient, so quite easy. The whole thing is unsupervised. You don't need labels. However, of course, the results are usually not deterministic. So partitioning clustering results are dependent on initialization. So from different initializations, you get different features spaces. Maybe a problem, maybe not. Representatives are usually unstable for different clustering methods and parameters. Well, mean is less stable than Medoid, for example. So this is another argument for using the Medoid here, because outliers in the clusters will heavily affect the mean, but less the Medoid. Yeah, and the methods typically capture pairwise correlations and dependencies, because if you use Pearson correlation, it's just pairwise correlation. Multiple dependencies are typically also not considered here. Yeah, but okay, there's a price you have to pay. But that just, I mean, those discussion slides are always, as I told you before, important that you just know what are the limitations of each of the methods, so that you can judge which of the methods do you want to employ or not. Yeah, just a summary for this week here. So we had forward selection, which examines each dimension separately, selects the k-best to span the target space, so very easy bottom-up approach. We had these greedy selections based on different measures like information gain, chi-square statistics, mutual information. Yeah, problem is we only consider each dimension, each feature individually, no correlations among features, or no relationships among features. Backward elimination the other way around. We start with the complete feature space and remove one by one the worst dimensions. The greedy approach uses model-based or nearest neighbor-based approach or distance-based approaches, which are not monotonic. If you have monotonic things or measures, you can use branch and bound search. For example, we had this example here with inconsistency, which was more or less only applicable for binary or discrete valued data. And then we had this k-dimensional projections, where we try to directly search for k-dimensional subspaces. So we directly explore the n over k subspaces, k-dimensional subspaces. And if this n over k is too large, we can employ some kind of random projections, for example, using genetic algorithms, or we can use feature clustering, which is also kind of randomized search, because you know that k-means, k-medoid are approximate random-based things, especially if you use a random initialization. Yeah. So this is the big picture of this week. Yeah, I hope you enjoyed this week. Next week, oh no, sorry, here, feature selection discussion goes on. I'm sorry for that, I was too quick. So yeah, just keep in mind many algorithms are based on different heuristics. Most of them are based on heuristics. There are two reasons to delete features. We want to get rid of redundant features. We want to get rid of correlations of irrelevant features. That means they do not have any correlation to the target value. Especially if we are in the supervised scenario, we can explore on that. Yeah, often even approximate results are quite good and increase the efficiency and the quality of supervised learning afterwards. So it's always a good idea to at least try out feature selection if you have a lot of features. However, yeah, the caution here, selected features need not to have a causal connection to the target value. But both might depend on the same mechanisms in the data space. So there may be some hidden variables which are not measured, hidden features that are not there. In that case, of course, you may be misled by feature selection, or also by better whole learning, of course. Yeah, and then there may be, of course, different indicators to consider in the comparison of before and after selection performance. So, for example, there may be different indicators that gives you the idea if the selection was good, the feature selection was good or not. Yeah, for example, model performance could be an indicator. Time could be an indicator. The resulting dimensionality, of course, can be an indicator, which is usually controlled by the input parameter anyway. But those are different indicators that can be important to evaluate whether or not the feature selection makes sense or not. Yeah, so always keep that in mind, that feature selection is always a good idea to try out, but you should consider it as this: try it out and see what happens, and try to evaluate if it really pays off or not. Yeah, that's very important, I think. So now we are at the end of this subsection 3 of, or section 3 of lecture 2. So this was week 3 on feature selection. Here are some further readings. I hope you enjoyed this lecture, and we will see next week. We will have a look at feature reduction. So in the next week we will also derive new features. So far in the feature selection we worked with the original features, and now next week we will also derive new features. Hope to talk to you next week. Stay tuned, stay healthy, and see you there.